In this video, we will prove Banach's fixed point theorem, which states that every contraction of a complete metric space has a unique fixed point. Here is how the proof goes. First of all, we fix a point, A in X, and then we define a sequence obtained by applying f to A indefinitely many times. So P0 equals A, and Pn plus 1 equals f of Pn, where n is any integer bigger than or equal to 0. Then we get a sequence Pn, and we want to show that this sequence Pn is a closure sequence. First step is to look at the distance between two adjacent points in this sequence. d of Pn plus 1 and Pn is equal to d of Pn plus 1 is f Pn, and Pn is f of Pn minus 1. And because f is a contraction, this is less than or equal to lambda times d of Pn, Pn minus 1. And then inductively, we repeat the same process. We will get less than or equal to lambda to the power n times d of P1, P0. Now notice that P0 is given. It is equal to A, and f is also a given function. So P1 being f of P0 is also known. So this guy is known, and I call this C. This is equal to C times lambda n. Okay, this is true for all n. Okay, and then for any n bigger than or equal to m, the distance between Pn and Pm, what you need to do, the usual trick is that you insert the middle points between n and m. So this is less than or equal, and then apply triangle inequality. This is less than or equal to sum k from m to n minus 1, d of pk plus 1, pk. And by this inequality, less than or equal to this, so you know that each term is less than or equal to c times lambda k. Now c is a constant, you can take it out, lambda k, and certainly this is less than sum k from m to infinity lambda k. Now this guy is a geometric series with common ratio lambda, which is strictly less than 1. So it is convergent, and the whole thing is equal to c times lambda m over 1 minus lambda. Now notice that since lambda less than 0 less than 1, so you know that this thing tends to 0 as m tend to infinity. So in other words, the sequence Pn is a closure sequence. Now because X is complete, you know that the closure sequence Pn converges to sum P in X. Okay, and then we claim that this P, the limit of the sequence, P is a fixed point. And the proof is very simple, straightforward. All you need to do is to notice the defining equation for Pn. So Pn plus 1 equals Fpn. You take limit on both sides. Get this? And limit of Pn plus 1 is the same as limit of Pn equals P. On the right hand side, because f is continuous, the limit of f is equal to f of limit. But limit of Pn is P, so this is equal to Fp. And so that means P is equal to Fp, and so P is a fixed point. Now finally, for the uniqueness, once again, it is easy to show. So the standard trick, all you need to do is to suppose Q is another point not equal to P in X, such that it is a fixed point of Q, of the F. And let's see what happens. You see this trick several times already. dpq is equal to, because P is a fixed point, P is equal to Fp, Q is a fixed point, Q equals Fq, and then F is a contraction, this is less than or equal to lambda times dpq, but the contraction constant lambda is less than 1, strictly less than 1, so this is strictly less than pq, which is impossible. And this contradiction shows that P is equal to Q, and that concludes the proof, because it shows that the fixed point is unique. Okay.